How thick is an image? Looking at an image on a screen, like for example, a YouTube thumbnail, you might be inclined to think that images are fundamentally two-dimensional. After all, they are flat, but that's actually not the case. Nothing in our universe is truly flat. Even the thinnest things we know of, single-atom-wide monoatomic materials like graphene, still have a definable depth and thickness to them, that being about 1/3 of a nanometer, if you're curious. This rule also applies to images. They are, in fact, three-dimensional phenomena, like everything else in our universe, which means they have a depth which we can measure or estimate. But how is that possible? Images are just packets of photons hitting our eyes in a coordinated pattern, are they not? Well, there is more to an image than just being a beam of light. In fact, there's really no such thing as a beam of light in general. Atoms do not emit photons continuously, i.e., light does not pour out from a light bulb or an LED constantly. The way images are generated, the way light is produced, is through the excitation of atoms, which can only occur in bursts. In the simplest case, let's imagine a light bulb with a single atom emitter. In this case, let's imagine it's an atom of carbon. The carbon is energized by some hypothetical mechanism, maybe it's heated up, and this energization provides excess energy to the electron shell of the carbon, which rapidly spits the extra energy out as a photon, or light. This emission of light in excited carbon occurs within 1 to 10 nanoseconds at most, and it only happens once per discrete excitation, meaning the carbon won't emit another photon unless it is excited again. Thus, the light is not continuously on, it's flashing. This flashing is as much the case in a single atom as it is in a collection of 1 trillion. If you increase the number of carbon atoms, you can create the illusion of continuity by always having a different atom emitting, but there is downtime between the photons emitted by any given single atom. If you're curious, for carbon, it takes about 6.9 or 7 atoms at maximum excitation potential to create an illusion of continuity. This brings us back to images. Images are merely the creation of coordinated light. Dictionary.com defines an image as a physical likeness or representation of a person, animal, or thing. So in short, an image with respect to light is any light arranged in a pattern to represent something. So, a flashlight beam on its own is not an image, unless you're trying to represent a circle. But if I arrange flashlights into the shape of a smile, I have created an image generator, with a projected smile being the image. If I fire my smile projector once, a set of photons in the shape of the smile will emit from the excited atoms making up the projector outwards at the speed of light. While that is extremely fast, it's as fast as it gets, it is not instantaneous. Thus, the smile has physical properties while it transits. This smile-shaped group of photons is the image, at least to my mind. Thus, the dimensions of this structure of barreling photons are in fact a valid interpretation of the dimensions of the image. And therefore, the thickness of this structure in the z dimension is the thickness of our image. It is the third dimension to its physicality. Two caveats before we continue. One, it should be noted that it is fundamentally impossible for any two carbon atoms in a structure like this to be excited and emit their photon at the exact same moment. Which means the image actually consists of photons offset from one another in the z-axis. To me, this does not make the image fundamentally non-contiguous, it merely gives it a slightly unintuitive depth. The image consists of a discrete set of photons that make up its structure, in until the last photon in the array of emitters is emitted, the image has not been fully transmitted, and thus its physical thickness widens with the gap between the photons. The longer it takes between the first photon emitted and the last photon emitted, the longer or wider or thicker the image is. This also necessarily means no emitter emits the same thickness image twice. There are always subtle differences and fluctuations. Second, and more importantly, the same atom does not emit any two photons from exactly the same part of its electron shell. Photons percolate out of the electron shell from relatively random positions, and a clustering of atoms will emit photons when excited from various depths, which essentially means that most atoms, even at identical distances, from their shared photon target, will have differences in how close their photons are emitted to that ultimate target. If we imagine a sheet of flat carbon atoms emitting photons as they would in, say, the earliest light bulbs, the photons are emitting outward from the sheet with as much variance in distance as the diameter of the electron shell. One photon may be emitted from a part of the electron shell much closer to the target, while another photon may be emitted from a part of the electron shell at the farthest distance possible from the target. These facts mean that at a minimum, such as in the hypothetical case of, let's imagine, simultaneous emission for all photons in an image, the image is still likely at least as thick as the diameter of the atoms from which the photons composing the image are initially emitted, because some of the photons will have been emitted from the far end of the electron shell, while others will have been emitted from the near side of the electron shell. Since photons themselves do not have a definitive volume, the volume of the image in flight or in transit, that is, the thickness of that plate of flying photons, can only be derived from the distances between the discrete photons within the image structure. Thus, we have, after much explanation, arrived finally at our first definitive means for measuring how thick an image is. In the case of our carbon atom smiley face image generator, we can choose to measure the image thickness as the distance between the first photon released and the last photon released in the given image set, and in this hypothetical case, our image has a thickness of 48 millimeters. Now, of course, this is not representative of any real setup, but it lets us visualize what the distance would look like in the z-axis. Now, I anticipate some people are going to reject this interpretation of image thickness. They may contend that the image itself is really only as thick as the thickness of the emitter medium, and the delay stretch in emissions of photons is less a physical property of the image and more an artifact of physics. However, I prefer the first definition. I prefer it because the measure of thickness reflects the dimensions of the image as it transits through space. And I think that that is an accurate reflection of what the image is when you're looking at it. But I concede the latter definition has merit insofar as it reflects in some way the intended dimensions of the image. That is to say, the depth of the emitter medium is a reflection of all the possible positions from which the transiting image, or rather the photons making up the transiting image, can originate. And so its dimensions reflect the ideal possible dimension of any given image generated from that source under our ideal simultaneous emission condition, and does not represent the somewhat random case-to-case spread of photons emitted by the natural variances in the half-life of excitation. If you take the first view, as I do, then every image emitted from an emitter is slightly different. If you take the second view, then the image is fundamentally fixed dimensionally in its thickness to the dimensions of the emitter. In the first case, where image depth is determined by the distance between the first and the last photon in the image emitted, then the typical image you see on a computer screen has a somewhat surprising depth of about 0.9 meters, which is roughly the height of a very large adult velociraptor, which is cool. This is because while the majority of photons are emitted within 1 nanosecond of excitation, enough excited atoms will hold on to their photon for long enough such that the total emission time for a typical computer image, or rather a typical computer image single photon plate, to emit will stretch to about 3 nanoseconds. And while that is extremely fast for us, 3 nanoseconds is an eternity in light speed terms. And that means that the actual image, the spread of photons, is about as far as 1 meter. This means that in most cases, the first photons from an image on your screen will have long since collided with your eyes before the last ones are even emitted. But of course, the nanosecond time frame is so fast that from our perspective, nothing changes. On the other hand, if you are one of those people who considers the depth to instead be the depth of the actual emitter material, then the average image is only as thick as the emitter, and the average emitter in a screen is really only about 50 nanometers thick. That is more than 1,000 times thinner than a human hair. And while it doesn't represent the photons in flight, it does get closer to the idea of a two-dimensional flat plane such as we perceive. But this raises, philosophically, another possible interpretation to image dimensions beyond the governance of hardware. Some people may argue, and I'll say they argue this with reason, that images are only important insofar as they are received. That is to say, if an image is generated and no one sees it to interpret it, was it really an image, or was it just light? Personally, I do think it was an image, but you may not. And it's an interesting direction to go in, because our eyes are actually very unique pieces of equipment. When we receive light into our eyes, that light is absorbed by specialized cells called photoreceptors, which reverse the process of atom to photon emission by absorbing photons and translating these absorptions into neural signals, which we use to see. So, an image emitted from a screen transits through the air and collides with cells in your eye to finally generate a mental image, something comprehensible. The translation from raw light to an interpretable proper noun happens in a small squishy orb in your skull, so it might be argued that the image doesn't even exist until that point of optical contact. In my opinion, it's a bit of a solipsistic argument, but let's run with it. Visible light photons do not contact the back of our eye in a 2D manner, of course. Remember, there is no two-dimensional in this universe. Everything is three-dimensional. Visible light photons actually have to interact with multiple layers of organic hardware before finally petering out. They will penetrate to the back wall of the eye to a specific and predictable depth. Interacting with these atoms in our eye, they will transfer their energy and their information to generate an image in our mind. On the back of your eye, for any given 1 degree of visual angle taken up on the sphere of your eyeball's rear, the retinal image is about 0.3 millimeters wide and extends to a depth of about 0.025 millimeters, or 25,000 to 40,000 nanometers, backwards into the photoreceptor cells. So, if you look at a given 1 centimeter by 1 centimeter square on a screen, that square will actually manifest photonically in the back of your eyeball as a curvilinear quadrilateral, which is apparently what this shape is called. Essentially, the last time the image exists before it is translated into its neural equivalent, it does so by interacting with your eye in a specific depth range, generating a specific shape. For me, writing this script, or reading it rather, I've measured the distance to the square on the screen that you and I are both looking at to be about 33 inches away, or 83.82 centimeters from my eyeballs. Which means the 1 by 1 centimeter square is presently a curvilinear quadrilateral inside my eye with dimensions of 0.2 millimeters square by x and y, and a maximum assumed z-axis depth of 0.04 millimeters, which is about a 97.83% reduction in square size from the version on the screen to the actual version I interact with inside my eye. This means, in practical terms, if you're out on the street and you see any given person, if they're about 2 meters or 6 feet away from you, their image in your eye will be no larger than an aspirin tablet, less than 1.5 centimeters tall on your photoreceptors. As an example, my friend Colin is about 6'2", or 187 centimeters. When he's standing 2 meters away from me, he exists as an image inside my eye, about 1.598 centimeters in length, which is coincidentally almost the size of the square I showed you earlier. Further, because the image, or the image of Colin in this case, has depth, remember the light is activating photoreceptors in my eye to a depth of about 0.02 to 0.04 millimeters, this means Colin shrinks volumetrically as well. Having been rendered curvilinear, he is now a volume of 0.05 cubic millimeters, or 54 nanoliters, which is a 99.9 and 7 more trailing 9% reduction in volume. So, if I wished to fill a 250 milliliter cup with retinal curvilinear Collins, I would need about 4.6 million of them, which is roughly the population of Louisiana, and far more Collins than I would be able to reasonably be a good friend to. And that's a lot of birthday parties to keep track of. Or really, the same birthday party 4.6 million times, which is somewhat more stressful, I think. So, to wrap it all up, how thick is an image? Well, it depends on how you look at it. If you believe the image to be as thick as the distance between the photons that make it up, then the images you're looking at right now are as thick as a meter, which is as thick as the walls in certain medieval castles. If you believe that images are only as thick as the width they actually take up inside of your eye, then images are about half the width of a human hair. And if you believe that images are only as thick as the substances from which they are emitted, then images are typically very, very thin indeed. As thin as 50 nanometers commonly, but possibly, thanks to the advances of modern science, as thin as a single nanometer, or even slightly thinner. Anyhow, thanks for watching. This isn't a history video like the previous two I posted, but I have more content planned like this, so I hope you liked it, and I'll see you on the next one.